Okay, thank you for your attention. And I think I already got some lessons from the video, but we want more lessons from the speaker. So let's welcome the Professor Thomas Kailath.
Thank you for coming this afternoon, and I want you to learn something from this lecture. Okay, so just a remark on that video. You know, the ceremony is half an hour. For the 10 medals are given for science in all fields of science, and occasionally for engineering, so I was lucky to have that. But my 80th birthday was last year, and we had a reunion of many of my students. About 50 of them came and presented papers at a conference that Professor Kwon was kind enough to attend. And they commissioned a videographer to extract from the half hour of Obama's speech the portions that were relevant to me. So there were many brilliant people whose work was mentioned, but so you saw only a little bit of it here. Now, let me talk about my connections to this lecture and to Korea. They started in 1980 when, after about 8 or 10 years of work, I finished my book on linear systems, which came about because when I entered the field of control theory, which was, I first started in information theory and stochastic processes, and then because of the need to study Kalman filtering from some of those problems, I started to enter control theory, taught by my students. Which is, I found, much easier way of learning by having them tell you what the subject is, and then you have a chance to ask them questions and get to the heart of the matter. So I found in entering that field that the textbooks in the linear systems field, I didn't find very useful for me, because many of the books, quite popular, the first 6 chapters were all about mathematics, differential equations, linear algebra, matrices. And then it took half the semester to start to talk about the applications. So I thought it would be useful to write a book which provided more motivation right from the beginning and introduce the mathematics and new ideas one by one, and each time illustrate them with some particular problem where that concept was very useful. So this book got a good reception, but after having taught it for many years, in 1980 when the book got published, I taught it for 1 year and then started to do something else. But the first person who taught the lectures at Stanford from this book for two quarters was Professor Kwon. He was a visitor on sabbatical from SNU to Stanford, and I gave him this challenging task, which he, I think, enjoyed, right? And he came back and he taught this course. Maybe some of you took it. And then Professor Ko, MS Ko, also started the course, and I believe he enjoyed it very much because he sent me some pages from his the tributes that were made to him when he retired, and he had nice remarks that he enjoyed teaching from the book. So I have a soft corner for Professor Kwon and for Korea. But so my first visit to Korea was to visit Professor Kwon was in 1987. And since then I've had several visits, at least half a dozen or more. 2 years ago I was 2 weeks at KAIST talking about one of the mathematical topics here. And I must say, it's remarkable the progress in the last 30 years in Korea. In 1986-87, you know, Samsung was importing engineers from Silicon Valley to help them do things. The country, the infrastructure was not the same as it is now. But you know, in less than 30 years, Korea has established a leadership position in several different fields. And in education, I mean, it is one of the very few countries where there is 100% literacy. And I read recently that it's the country which has the highest number of university graduates per population. And, so it's thanks to the people like the people here, the professors, who inspire young minds to go out and do these things. And Professor Shim was talking about what has happened in the last 70 years at SNU. I think the next 70 years are going to be even more glorious. And I'm very happy to be here for the first lecture and the 70th anniversary. So thank you all. Acknowledgements briefly. This lecture was, of course, invited by Professor Kwon and his students who endowed this lecture. But Professor Shim has been one who carried all the administrative burden. And I must say it was a great pleasure. I would have various questions of different kinds. And I don't know if you ever sleep, but the answers came back almost immediately. And everything has gone very well. I've enjoyed my stay here, and including in your fine guest house. So let me tell you about this very presumptuous title, It happened as follows. About a couple of years ago, one day I got an email from someone in Ecuador whom I hadn't heard of, saying that every year in Latin America, they have a convention of all the engineering schools in the Caribbean and Latin America. And this year, the convention is going to be in Ecuador. And there'll be about 1,000 people, and they would like me to give the keynote lecture. But then they added, we will fly you first class, and at the end of this conference, we will give you a 5 days holiday in the Galapagos Islands. Now, for many years, I was probably 78 or something. It was my wish and my late wife's wish to go to Galapagos Islands. So this seemed like, so I replied, I said, that's interesting, but I should tell you that I'm recently remarried. Next email, she can come with you. Then I asked them, what do you want me to talk about? And that's when they suggested this title. And I replied, I have never given a talk like this, because I usually give somewhat technical talks on specific topics. But, they persisted. They said, you have worked in different fields, as you heard, and you must have had various experiences. And you can consult with your colleagues and try to tell us what are some of the things that lead to breakthroughs. And so that's how it came about. And you will see whether something useful has come out of it from this talk. Now, there are two types of breakthroughs. Really revolutionary breakthroughs made by geniuses. They do things that nobody had ever imagined before. I just picked, there's quantum theory, there's relativity, and so on. But I just picked examples in engineering. Norbert Wiener, he was the first to introduce a statistical view of communications and to say that in engineering problems, it should not be just by trial and error and by seat of the pants. You should set up an optimization criterion and try to find a solution that's best or approximately best under the criterion. And that led to all these developments in signal processing, estimation, control. And of course, he became famous because he said that the ideas of feedback are universal in human life also. And cybernetics became a buzzword. And I was asking somebody, now they have cyber physical systems, whatever that is. Information theory, similarly. Nobody imagined that when you have a noisy communication channel, you can send information at a non-zero rate and get as accurately as you want. Because people always thought that if you have a noisy channel, you must keep repeating the signal so that you begin to understand it better. And if you want perfect accuracy, you must repeat it infinitely often, which means the transmission rate is 0. So he said, no, that's not true. You can send at a non-zero rate of transmission of information and get whatever accuracy you imagine. And that was published in 48. It seemed a dream. I went to MIT 10 years, almost 10 years later, with a very brilliant group of people in information theory, many of whom are well-known figures in the field, including the founder of Qualcomm, for example, Irwin Jacobs. And we thought, why are we studying this mathematical abstract subject? Oh, it's like in the old days in Europe, people studied Latin and Greek, not because it was useful, for training for the mind. So information theory is training for our mind. But as you heard the president say, you know, we were hopeful that sometimes you could actually make these things practical. And the development of technology, especially integrated circuit technology, has made all the dreams of information theory possible. And now we are in a cell phone communication sending at the theoretical limits in such very compact devices. Okay. So in a different way, Steve Jobs imagined the possibilities of a smartphone. And now we have computers in our pocket and things like that. So that's genius and revolutionary breakthroughs. But there are ordinary breakthroughs, which happens when you work on a problem, and many of you will have had these experiences yourself. You find a way of doing things that's very different from what people believed, and you are able to overcome some limits that people thought were inevitable, and you found a way of breaking those limits. So those are minor breakthroughs which, as I said, in all of our experiences, you'll have some of them. And I like Thomas Edison was one of the world's greatest inventors. I think they said from his lab there was one new invention a week, including all major ones, of course, that you know about. And he has this, what is the characterization of genius? 1% inspiration and 99% perspiration. Okay, so there are no magic rules. Okay, but I was inspired by how does a Harvard Business School teach business strengths and rules and so on to people? By case histories. They examine different companies, what their failures, their successes. So I'm trying to give you some case histories where some of these minor breakthroughs have been made. And I want you, as you listen, they are mostly stories, and they don't need much background because you are also from different fields. But as you listen to those stories, think what is it that is special about how the results in those stories came about, and what insights can you gain from them in the process of doing this kind of research. And at the end of my talk, I'll try to make a list of these. But as I talk, please think in your mind, what was it that made this happen? Now, you know, one should say, in our work, we don't start out saying, oh, I'm going to make a breakthrough in this field. You do the work, and it happens sometimes that you do something which can be classified as a breakthrough. Okay. And my examples are from electrical engineering, which is fine for this audience. So I will go through briefly a few examples. GPS, which I saw one of the latest applications here, Professor Seo, and this automatic autopilot driving around the campus. Okay. And there's a reason I included that, often I don't. Then I'll give you an example from VLSI, from semiconductor manufacturing. It's called rapid thermal processing. From DSL, you know, broadband wireline communications, and optical microlithography, where people believed that with optical techniques, you could not make transistors with line width smaller than 100 nanometers. Okay. Well, we broke that barrier. So, are you able to hear me? Okay. So what was GPS? You know, an all-weather worldwide real-time system for accurate position location, huge number of users, both commercial and military, at almost zero cost to the users. Okay. That is quite a challenge. And two people, one who passed away now, Ivar Getting, and a young Air Force officer, Brad Parkinson, had worked together and came up with the idea that you can have satellites which will send signals, and by measuring the time differences of arrival from different satellites, you can find your position. So he tried to tell the Air Force to invest in this. They thought this foolish. He said, you know, you can deliver weapons, you can hit targets very accurately if you have GPS. They were not so interested in that, and they had absolutely no interest in the civilian applications. Okay. And also it seemed impossible to do that in the mid-70s. But as one of the developers, whose name I'll mention, he was partly at Stanford, Jim Spilker, he said, sometimes doors that seem closed open when new possibilities arise, when new technologies arise. So, you know, new families of codes became available. Early supercomputers were getting cheaply made. You had very high precision clocks because that's needed for accurate time information. And the satellites have to be very precisely maintained in orbit and so on. So all these things happened. And so these are some of the pictures here. For example, I lost the pointer. Oh, it's here. This is Brad Parkinson making a presentation. These are satellites sending signals. They now want to have about 400 satellites, by the way, around the Earth for GPS. This is Jim Spilker, who was the chief scientist for the GPS effort. Brad Parkinson and he came to Stanford to do this effort. This building behind is called the Spilker Building because he and his wife were very successful investors, and he started a company, Stanford Telecom, and he donated, you know, $30–40 million to have this beautiful building. So sometimes the breakthroughs can have financial value as well. So very briefly, you know, you need accurate, precise location and clock time of the signals. Moreover, there's many satellites. The signals should not interfere with each other. So you have to carefully design the signals so that they don't get disturbed by the other signals. So the system that he built, the key thing is, you know, 24 satellites, the error is 7 millimeters, okay? Not centimeters, millimeters, 7. And in order to do that, he had to use both general and special relativity. Because, you know, special relativity says that when you measure time in a moving object, it's slower than on the Earth when it's stationary. Now, when you want very fine accuracy, you have to correct for that. The speed on the moving satellite has to be adjusted because of the relativistic effect. So he did all that and came up with this theory. So it's, you know, and now, I mean, cheaply almost, you can get a GPS on your, I use now only Google Maps for GPS, okay, so it's a freebie. I entered the field of VLSI in an indirect way. You know, most of my work was information theory, statistics, control theory. It's quite mathematical. And there were some breakthroughs there, but that's harder to describe. But Stanford, you know, is sometimes people say is, Fred Terman is the father of Silicon Valley. And Stanford started in 1955 to build up the department in semiconductors. And Shockley had come, who was the inventor, one of the inventors of the transistor, to Stanford. And so Stanford always had a strong presence in semiconductor technology. But the far-seeing chairman, John Linville, some of you in that field know his books and his work, said, you know, we want to do VLSI. At that time, the technologies were LSI, large-scale integration, with 100,000 transistors on a chip. Let's have a dream of 1 million transistors on a chip. But you have to bring new technologies for this, and you also need to find applications. What do you do with 1 million transistors on a chip? So they said, so we made a team of people from solid-state technology, semiconductor circuit design, computer science, and information systems, because I was on the executive committee of the department where this was discussed. And I said, well, in image processing and signal processing, you need lots of processing powers, so maybe we can use 1 million transistors on the chip. So the 4 of us made different presentations to industry and raised quite a bit of money to have this Center for Integrated Systems at Stanford, which is still going, and so on. And DARPA got, this is the Defense Advanced Research Projects Agency, which has funded many, many new developments, as you know, stealth aircraft, artificial intelligence, which is now all the rage. And we got them interested in VLSI. And the very first VLSI contract in America was given to a team of 3 people, Forrest Baskett from computer science, he's sort of the inventor of the workstation, myself, and Jim Meindl, who is well known in the semiconductor field. So that's the thing. So then I had to try to deliver my promise that signal processing could use these 1 million transistors. So how do we do it? I had no background in VLSI at all. Okay, it's a new field to me. I hired 3 new students, 2 from India and 1 from Spain. And fortunately, very luckily, at that time, a chemical engineering student from Santa Barbara wrote to me saying, can I be a postdoc with you? Now, Santa Barbara has a strong group in control theory for semiconductors and so on. So that was very good because, when you're working with transistors, there's a lot of chemical jargon that one needs. Oxidation, rapid thermal, this and that, and polysilicon. I don't know all the jargon that there is, but he was able to help us. So starting with nothing, we began to study this subject. And actually, these 3 new students, after 4 years, all graduated. We discussed together, but they all finally got different thesis topics. And Bell Labs hired all 3 of them in the same year. Because Bell Labs at that time, now the Bell Labs is different, they would send a recruiter to campus to follow the kind of work going on, talk to different students and so on. So this recruiter, Scott Knauer, he liked these 3 students, and he said, it's a bit difficult, but I want to hire all 3 of them. And he went back and told his boss, who said, no other fish in the ocean. So just to show off a bit, he said, oh, well, Kailath students all do 3 theses, 3 PhD theses by the time they are done. So take a risk. And actually, it worked out. Okay. One of them, Sailesh Rao, his thesis was on how to do special purpose, how to put signal processing algorithms on a VLSI chip. Because the VLSI chips are interesting. Each chip, each transistor is connected only to its neighbors. Okay, that's the design pattern. So that's not the usual architecture for signal processing. So how do you do things like Fourier transform, matrix multiplication, and so on, when you have these constraints of nearest neighbor connections? Okay. So Sailesh Rao did a thesis on this, a mathematical thesis. He found some paper in computer science called Regular Iterative Algorithms by Richard Karp, who is a big name in computers. And he applied that and integer programming and so on, and that was his thesis. He went to work in the electronics side of Bell Labs, a home Dell, and he was working there when he heard that HD TV at that time was the big challenge, because Japanese were dominating the electronics field, and America wanted to, do something which would be different. So they said high definition television. So a lot of money went to that, and Bell Labs was there. But he heard that the designers with 10, 15 years experience were unable to meet the specifications, area limitation, power limitation on the chips, HDTV chips. So Sailesh said to his partner, Iranian working with him, Mehdi Hatamian, you know, my thesis was on how to design chips for such things. Let's tell our boss and we shall try to crack it ourselves. In probably less than 6 months, they found a solution which, and I can't remember the numbers, and there was a special issue of the Homedale magazine, which he can't find and I can't find, with his picture on the cover showing the chip, which, so the numbers I don't remember, 3/4 the area, 2/3 the power, and designed in 6 months. Okay. So people were astonished. Here are engineers with 10 or 15 years experience unable to do it, because they are largely doing by trial and error, whereas he had a theory and he was able to adapt the theory to it. So that was the HDTV challenge. So then soon the other groups would come and say, this chip is going to be the next most important chip in Bell Labs history, so please help design it for us. After they did a few of these, they said, why are we doing this on a Bell Labs salary? And though Bell Labs raised their salary and so on, they said, no, we are leaving. And they formed this company, Signal Design Experts Incorporated. And Bob Lucky, whom some of you know, he was the executive director in that communications. He said, okay, we are treating you very well. You're top of the scale. If you leave, we won't give you any work. So, you find something to do yourselves. Within 6 months, Bell Labs was giving them contracts. And within 3 years, they were acquired by Level 1, and Level 1 at a good price, actually. And the two other students, let me tell you, one of them went to work in the math group at Murray Hill and Bell Labs. He is one of the world's experts in databases now. Very different from his VLSI work, but we feel that we can enter any field that you want to if you work hard enough. And the third student was somewhat unique. He was more interested in management than engineering. And he somewhat reluctantly did his thesis. It wasn't very good, and I finally, but he got help from his other colleagues to do the work. So I told him, I'll sign your thesis if you promise not to work in this field anymore. He went to join the venture group in Bell Labs. And then he joined Signal Design Experts as their marketing officer and did very well. Okay. So, there are some lessons from this experience which you may get. Now, a few years later, I entered semiconductor manufacturing, totally different to me. How did that happen? Lucky accident. I told you I do work in mathematics also, and so I go to math conferences, and we had new results in linear algebra. And I met a mathematician, a famous professor at City University of New York, Einstein professor, I think. He heard this talk. He was what we call a streetwise mathematician. Many mathematicians can only talk to them in their language. They don't quite understand what you are trying to say, or they don't want to make the effort. He was willing. He was a consultant to IBM and so on. He said, your work is interesting. I'm going to DARPA to head them. We are starting a new mathematics program. I started already, and it's not doing too well. So DARPA said, since it was your idea, you come and run it. So he said, when I go to DARPA, send me a white paper and I'll see what I can do. Now, most of my work is from NSF and Air Force Office of $50,000, $100,000. DARPA doesn't like small contracts. They give you big money because they have very small staff. They just want to try big things. So I thought that's great. For mathematics, we get, large sums of money. By the way, there's a joke when VLSI was being formed when people say, what is VLSI? very large-scale integration, but our joke was very large source of income. Okay, but that was, I hadn't heard from him for nearly 2 years. One day I get a call from him, and I pick up the phone and says, "Hello, Tom, this is Lou Auslander." "Oh, Lou, where have you been?" "Oh," he says, "a long story, and I won't repeat it here. But finally, I'm at DARPA. There's a lot of red tape in the government because he had a very high salary and they had to adjust all that. But I find that my predecessor has given away all the money for math this year, so I have no money for mathematics. Moreover, the mathematics program is moved from information technology to material science." He said, "I don't know why, but maybe the general thought, because the general runs DARPA, it's a military thing, all the M's should be together. So mathematics, materials, and so on." So he said, "I have no work. I just wander around listening to seminars and so on. And I find that they're working on composite materials, very elaborate materials for stealth aircraft, for light aircraft and all that. But they have no idea how to manufacture these. These are physicists and chemists, and the techniques that they are using are trial and error." He said it's like the old days when people used to make steel. The method was heat, beat, and hope. Okay, so he said, "I think control theory can have a role in it, signal processing, simulation, computation. They have no idea about these things. So I have no money for mathematics, but I can give you money for manufacturing." So I was silent for a little while. I said, "Lou, there's a true story, by the way. It came in print later. That's very kind," I said, "but I only write papers. And in manufacturing, you have to do something." So, but he persisted. He says, no. I believe that you can do it. And it's a long story, he says. But finally, he said, we give you, of course, significant amount of money. You pick any problem in manufacturing, and doesn't matter if you fail. So he gave us $2 million for 3 years and said, see what you can do. One thing I complained, I said, DARPA used to have monthly reports. I said, how can in university you do monthly reports? No. Annual report is okay for me. So, yeah. So what to do now? The Center for Integrated Systems that I mentioned earlier was doing work in semiconductors manufacturing. So I went over there, and a friend of mine, he had a project. They had already begun a project on a new way of manufacturing semiconductor chips called rapid thermal processing. Okay. What is rapid thermal processing? In 1990, Texas Instruments was given at that time, a large project, $150 million, to validate a new way of making semiconductors. And CIS at Stanford got a subcontract because the leader of the TI program was a Stanford student. So he asked his advisor to help. So what is the difference? You see, the fabs at the time made large volumes of a single part, DRAMs, SRAMs, so on, large throughput, huge cost. At that time, 1.5 billion. It was 500 million in 1990. Now it is more than 3 billion. Okay. And after 3 years, a new technology, so you have to change it. We are in the military. We don't need these large chips, which we can just purchase in the market, but we have special purpose applications. So we need special chips in small numbers, many different types and many different processes, but in small volume, say 1,000 wafers a month of ASICs. Okay. And the cost should be $50 million. Okay. So how does it work? What was the proposal? They said, what you should do is you have a little, for example, a cylinder, 1 foot diameter, or a box, a cube roughly that size, and you put a wafer, a robotic system in a vacuum, which puts a wafer inside this box. And then you have heat lamps on top, which the aim is to raise the temperature across the wafer from room temperature, say, to 1000 degrees quickly, okay. Then hold it uniform, constant across the whole wafer for 1 minute, 2 minutes, 3 minutes, depending on what process you are doing. You know, different oxidation, annealing, all that can be done one after the other in a box like this. And then cool it as quickly as you can, because if you cool it too slow, the throughput is low. Too fast, the wafer gets distorted, it bends. So do this, okay? That was the challenge. So what was the status of the field? People were trying to arrange the heating mechanism in different ways so that you got uniform heat flux over the whole wafer. Okay. They wanted the heat flux to be the same. To do that, they had different kinds of lamp structures. I only showed two. For example, a parabolic reflector. So you have a halogen lamp here. It reflects, and you try to get uniform heat along here. That doesn't work so well. So some people tried one array of lamps here, say, going into the board, and another below in the opposite direction, and try to work. Okay. Well, and there are other possibilities. Small companies used to make this, but none of those things worked. Okay. They were unsuccessful to get uniform temperature across the thing. So this is the problem that we discovered when I went to talk to CIS people. And I said, well, you know, this is a controls problem. So we think we can do it. Okay. And they say, oh, we have control. But that's control for semiconductor. They purchased from some company a black box, which is really a resistor with one knob, and you can adjust the heat with that. So we said, well, let us see what happens. So we used the systems approach, which many of you in the audience of control theorists now are familiar with. The old approach was trial and error, okay, empirical. And you know, a lot of semiconductor work is done in that way. Some intuition of physics and a lot of statistics of actual data. In system theory, you make a simple mathematical model by approximating the real world, okay, because the real world is too complicated to describe mathematically. So you make various assumptions and get a simple model which you can analyze. Okay. Then you use different techniques to solve that idealized problem. Okay. But the solution can be fairly complicated, so you must understand the solution, the mathematical solution, what actually does it mean, what is the physical meaning, so that you can make intelligent approximations to build a working system. Okay. That's the pattern which many of you have done in all your applications in model-based control, model-based signal processing, and so on. Oh, the word practical, I said, has many aspects, from technical feasibility to the cost. So what did we do? The disk is two-dimensional, but we said, let's start with a one-dimensional disk. You have a rod, and you heat it at one end and try to get uniform temperature after some time. Okay. We found it's not possible to do. Okay. It's wrong to make, this is the key thing. The mathematics showed that what you need is non-uniform heat flux over the wafer. Okay. There's some intuition behind that also, but first we got it mathematically. Moreover, you need multivariable control, not single variable control. Okay. So how to do it? Okay. We were lucky that a new lamp structure of two concentric rings of halogen bulbs were made through some new manufacturer. But both rings, both circles were tied together because you have only one controller. So we said break it and give independent control to each ring. and make a third bulb in the middle to allow 3 controllers. Okay. So this became available. And I'll just, this. Just to give you an outline, which is short. First we studied heat transfer. What are the problems? We had to make a mathematical model of the wafer, finite elements, and make the heat transfer calculations. And actually, I'll tell you, this work went quite well. And so by then Auslander had gone. His successor said, I want you to present your results to the director of DARPA. You have 15 minutes to tell him. Actually, he got so interested with 45 minutes. He's a mechanical engineer. So you'll like this story. He said, heat transfer, oh, did you work with people in the mechanical engineering department? Because I know them. I said, no, sir. I think the students went to the library and got some books on heat transfer and figured out what they did. Oh, I forgot, he said. Electrical engineers can do anything. So which is true. I mean, look at all the variety of things that electrical engineers do, from lasers to semiconductors, and yeah. So it took time, and we were lucky that I had the same postdoc, was not married. He would go back and forth to Texas Instruments and so on. And we made it successful at Stanford. We did 8 different processes, 13 different processes, 8 different machines, and we gave the technology, they call it the Stanford controller, and the demonstration was successful. Demonstration was produce 1,000 wafers continuously over a 5-day period. Okay. It worked. So, that was a success, but we were disappointed because somehow rapid thermal processing seemed to us was not popular. It didn't take off. But about 2 or 3 years ago, I was at a dinner with my semiconductor friend at his home, and I was talking to someone from AMD, Applied Micro Devices. And he said, oh, you're Kailath. We use your work. I said, on what? Rapid thermal processing. Because for many special aspects of the semiconductor process, they find it useful to use rapid thermal. So it's a big industry now, and there are companies making it. So many years later, this work became useful. Let me change subjects to DSL, which is the way we get broadband on wireline nowadays. The father of DSL is a former student of mine, John Chiaffi. He came from Bell Labs, actually. Bell Labs in those days would send students for masters and PhD and so on. So it's in 1979, as a young kid fresh out of Stanford, with his master's actually, I was laughed out of the room in my first DSL meeting when I pushed for more speed than the 160 kilobits per second that they thought was the limit. I said, because he had worked out the channel capacity, I mentioned information theory, when you work out the channel capacity of this telephone wire, it's 1.5 megabits per second. So we should be able to send at 1.5 megabits. They laughed at him, of course. Well, he pursued the technology. He found a source of money from some institute which was giving seed money to universities to develop new technologies. So he got some money there. With his students, he found a new way of modulation. And he's Italian. He formed a company called Amati to productize that technology. And later it was acquired by TI for a very good price. And but why was Amati successful? See, to have a product that works, you must have the standards, right? Because different people have to manufacture it, and all of them must have some common elements which all our devices must meet. So the standards body had a competition saying all technologies come and present, and we'll choose which is the best technology. So Bell Labs, Lucent actually, was one of the competitors in this field. Amati, a small company, and Bell Labs was too relaxed, I think. They said, who can match Bell Labs. It turns out that Amati did better than Bell Labs. So the standard was given to Amati, okay, which made Bell Labs very mad, of course. But so that's how Amati got started. And today DSL speeds are in megabits, okay, and DSL is is very successful on the broadband, apart from wireless. And he hopes to have gigabit per second for say up to 1 billion people and very high speeds for the rest of the world. Okay. So again, what lessons can you get from his experience? Okay. Final example is lithography. See, DARPA has one limitation. They give you money for 3 years, and after that you have to do something else. But this project of ours was so successful that the project monitor persuaded the director of DARPA to say, we should encourage, they set up a program called multi-university, multidisciplinary research projects to show the application of technology to manufacturing problems of all kinds. So 6 different proposals were granted in this field, and Stanford wanted to participate, but we can't do the previous work. So my interest is really more in signal processing than control, because I had forgotten my control theory by then. And we discovered that lithography, which is the process, I'll tell you in a minute if you don't know what it is, it's a printing process, that's lithography, was the bottleneck in semiconductor manufacturing. More than 1/3 to 1/2 of the cost is in this technology. For you have a light source and you want a particular pattern on the wafer of 1s and 0s. That's the lines on the chip. Okay. So how do you do it? You see, that is a binary pattern, 1s and 0s. Light is electromagnetic. At every point it's a complex amplitude and phase. Okay. So you have to make a mask, which is also a complex mask, complex amplitude and phase, which takes account of the nature of the light and the distortions in the lens system and so on, and tries to make a pattern which is different from the final pattern. You have a gap, that means there'll be no exposure, and if it's a blocked pattern, then that can be developed and so on. So this has to be different from the pattern that you want, and moreover it's complex. Okay. So that's the design problem of the mask. Okay. So what was the challenge? You see, when they started about, this is 1990s, the light source was 436 nanometers was the width of the electromagnetic illumination. And you were this is the line widths that you wanted were 456 nanometers in 1990s sometime. And the light source was 300 nanometers. Okay. So that's easy. It's like you have to draw a thick line with a thin pencil. You can just draw it. Okay. Then you made the lines, the source thinner, 2 micron, and you were able to, and they still kept lowering the 436 and so on. And finally, around 1990, they wanted 365 nanometers, and by then, oh no, I'm saying it wrong. This is the light source. Suddenly I got a mental block here. You want the width to be 200 nanometers, and you have half that size, the source. Okay? And then 365 source, and you are able to do 0.6, 600 nanometers, because this is half the thing. Okay? Then you get a crossover point, and 350 nanometers, and the source is 365. So now the pencil is thicker than the line. So what do? You may make some optical tricks to go below that, And so people were able to do 250 nanometers and 180 nanometers with what they call optical enhancement techniques. I think the laser people here and our chairman probably are aware of some techniques like that. But the aim was, the semiconductor roadmap, you have to go to, this was 15 nanometers by 2008. Now they're working on 10 and 7 actually. But how to do it? There's a sub-wavelength gap. Okay. Your pencil is thicker than the lines. Okay. So let me tell you, this was a challenge that we faced when we started to work in this field. Someone from Sematech made this presentation in a meeting. He says, through 180 nanometers, you'll use optics. In order to do that, you need some improvements in the exposure, the mask, and so on. The resist has to be different. So they will be needed to extend optical lithography to 250 nanometers and 180 nanometers. Okay. But below that, below 130, you have to use not optics. You may have to use E-beam, or people tried X-rays and so on. Okay. Or EUV, there's a technology which they were beginning to propose, still hasn't happened. So that was when we took this problem. So we made a proposal, multivariable control, simulation, optimization, and signal processing for the microlithography process. Okay. This is the pattern that you want. This is the pattern that you get from the traditional techniques. But in our preliminary work using signal processing ideas, we were able to get much cleaner patterns. So we showed that, and DARPA gave us the contract. So just to tell you how people felt, Bern Lin is a very senior technologist, member of National Academy of Engineering at TSMC, which is one of the best fabs in the world for making semiconductors. He said, I think microlithography will stay around 130 to 150 nanometers using optical lithography. And to go to 100 nanometers, we'll have to use E-beams, which is very slow process, E-beams. Okay. That limit is going to stand for a long, long time unless there's a significant breakthrough that nobody knows about, and at this moment, nobody anticipates. Okay. That was in 1997. Well, of course, Bern Lin didn't know that progress at Stanford had led us to form a small company from the PhD thesis in 1995 called Numerical Technologies. Okay. And we worked with Motorola, this company, and there was a news release in 1999, 2 years after Bern Lin. Motorola today announced the first successful fabrication of a 100 nanometer microprocessor using a standard 180 nanometer source. Fabrication was accomplished using some signal processing techniques, phase shifting, and OPC from Numerical Technologies. Okay. And then we went on, Lincoln Labs made 90, then 50, and then Intel acquired the technology from us. And now we don't know what they are doing, but they're making their own improvements. And they're going to, 14 is already in general production, 14 nanometers using 156 nanometer source. So I gave a talk at Princeton when this work was over, breaking the 100 nanometer barrier. This barrier was called by Gordon Moore, by the way, Moore's law. He said 100 nanometers is the barrier for this. Breaking the barrier via signal processing, and the subline is from doctoral research to Wall Street, because the thesis was published in 96 and the company went public in 2000. And so I explained, and there's no time now to show what we did actually, but we had to solve a nonlinear inverse problem. You have a pattern of ones and zeros, and you have a light source with its own aberrations and so on. You have to design a complex mask which will give you that desired pattern after correcting for the optics. Okay. Well, we found a solution. Actually, it uses the so-called famous four-color theorem of mathematics. There's a theorem. It took a long time to prove, and the proof is actually mathematical part of the way, and then it had 400 or something cases, which by a computer they showed could be solved. You know that if you have a map, 4 colors are enough to make neighbors distinct. Okay. That was used. So we showed that 4 phases are enough to do the technology and so on. So that's called double, anyway, it's used in the industry. How about the internet? Vint Cerf, who is one of the pioneers of the internet, once said that communication engineers thought that packet switching, on the internet you break up the data into packets and send it on the internet in different ways and reassemble it at the other end. Would not be able to handle speech or video because you have to store these packets till you collect them and then forward them. And how can you do streaming of real data on the internet? So it's impossible. Well, nowadays we are all watching Netflix and so on your TV screen. Okay. So skepticism and naysaying is not new. There's a story, by the way. What time is it? I'm over time. Yeah. Okay, just yeah. Oliver Heaviside is a famous person, a self-taught deaf engineer who taught himself mathematics and battled with the British Post Office about inductance loading of telegraph lines. People felt, he said the theory says that the usual lines are resistance and capacitance. You should add inductance. And the chief of the British Post Office said, that's stupid. You know that inductance slows things down. Okay, so how can it improve the speed? But he proved he was correct, actually. And then Pupin in America patented that idea. And there's a beautiful book about him called Sage and Solitude from IEEE Press. So finally, after all these stories, what are some of the guidelines that we can draw from it? And you may have your own and so on that you will take. The most difficult is you have to find the right problem. What's the definition of right problem? That depends on luck, on circumstances, on your intuition, what you bring from other fields, But all of you do that when you finally solve something. You found the right problem, okay? Trust your instincts. If you have certain ideas, people will tell you no, but beware of them. I mean, listen to them because they may be right and so on, and you can get some ideas, but persist with your ideas. Okay. Another thing very important for students, don't wait to start till you have all the prerequisites. Research students say, oh, I have to take this course, that course before. No, just jump in and try to do something in the beginning. And actually, I like a quote from Dr. Zhivago, the Soviet Russia. Man is born to live, not to prepare to live. Okay, so that's the message for research. Team up, there's power in groups. We found in all these topics, no one individual could do it. There are different people cooperating to do that. So I like to encourage my students to work together because you learn more from your fellow students than your professors, in a way. Because each student takes different courses and so on, you share that knowledge. So, and then eventually you find enough different material to get your thesis. Okay. We did that in VLSI, in lithography, in manufacturing. Have broad interests to be able to cross-apply tools and ideas from other fields. Okay. So I tell them, go listen to seminars in different fields. You may not understand most of it, but you may pick up something which will stick in your mind, and when you're following a problem, say, oh, I heard something which may be related. Okay. So, my work has often used ideas from communications, control signal processing in different problems. Okay. Be alert to opportunities and seize them. Even in my case, people said to me, aren't you afraid to enter a new field? Well, maybe I'm stupid, but as Obama said, I believe that you can learn something new and try to do something, and you'll find that your background can help you. Okay. But so be alert to opportunities and seize them. Don't let them go. Don't give up too soon. And in our case, there were many such examples in our work, where we were frustrated, but then something happened, and I'll tell you later. I could only have more time. And learn from failures, okay? Because you'll fail. But why did you fail? What happened? And so on. A final quote from Edison. Edison said, "I have not failed. I have found 10,000 ways that do not work." That's a message to keep in mind. Thank you.
So I think we may have 15 minutes to talk about your
By the way, I hope you were able to hear me. Nobody protested, because I was away from this. Yeah.
So could you please go back to the guideline, the last page of your slide? And upon this slide, I think we can share, right? So I know most of us, and actually all of us already made a small breakthrough.
Yeah,
Maybe
exactly.
it's big or small. Right?
No, I agree.
Yeah.
I
So
agree.
I think we can
that
share how we think, or we may have some secret guideline that is not mentioned in the list, or whatever. So we can share. So if you have some comment, question, or sharing your idea.
Give me your examples also.
Yeah. So we will deliver the microphone for you to talk.
It can happen in mathematical work also, by the way, these things. But that's harder to explain.
And my question is, when you yourself were like sure about your potential contribution on new project, sometimes it's difficult to do the same thing for your students. So how have you persuaded or motivated your students to work on new problems that they didn't care about before?
Well, if they want support, and I must tell you a story. Of these 3 VLSI students that I had, we had a reunion of about 50 of my former students came last year with Professor Kwon. And Jagadish, one of them, said, I learned, he worked with us on VLSI, and he's proud of that example. Now he works in database. He says, professor does not need to know more. He learned from that. Professor does not need to know more than the students. Because you learn along with them. And I always tell them, you have much more time than I do. So you can do a lot of reading, work and all that, and then come and tell me. And I will use my experience to ask you. Research is asking questions. That is the secret of research. Keep asking questions. Why is it this way? You give me a solution. Is that the best solution? What's the reason this is the solution? Can you try a different thing? And so on, okay? So my definition of when is a PhD student ready to graduate, when he or she is able to make their own questions. When they have the intuition, etc., to ask the questions and challenge a result that's put to them. Okay. So that's part of the secret of research. Have an inquiring mind and ask questions.
You are saying that team up is important. You recommend teaming up. So I think that includes collaboration with other professors. And I think it is always difficult to collaborate because of some overhead for collaboration. So how do you solve the problem of overhead in time and effort?
You see, and I haven't explained this, but you made a good point. I mean, without the large contract, we would not have been able to enter the VLSI field because we didn't know anything. But, we had a contract from DARPA, which enabled me to hire postdocs and have time to do that. So that's where the luck and, whatever your past reputation, all these things. So money is very important. Yeah, because you
I
need
agree.
time. You need time, and I mean that's what the quotation that I'm supposed to make. I don't remember it exactly, but what Obama said. You believe that if you work hard enough, you'll find something, but you need the time and the background and do that. So, and you heard luck comes into it also. I mean, the fact that a mathematician would ask me to work in manufacturing, that I agreed, it was luck, but and enough money.
Thank you.
And people who don't want you, I mean, I had some contracts where I said, this is what we propose to do. But as you do the research, different things happen, and you may not do what you promised to do. So I had one monitor once, he said, he was a bookkeeper, that you said you'll do this and this, but you haven't done it. You did something else. And so I said, well, that was the interesting problem to solve, and the results were good, so you should not be unhappy. But not everybody agrees.
Would you kindly tell us more detail about your way, how to find the right problem?
No. I mean, for example, manufacturing, when we first went. There are many problems in manufacturing that need a lot of background. You have to handle, very expensive equipment, electron scanning microscope and so on, and people won't let you touch their equipment because if you are not in that field, so on. So what was the point I'm trying to make? Yeah, and then often there are hazardous materials in manufacturing. But we found a problem that had no dangers of that kind, This box cannot explode, and we are not directly dealing with all the gases and all that go through the system. So we were lucky that at that time there was a project in manufacturing which was also, reasonably safe, but which was adapted to control theory, which we knew about, which the semiconductor engineers didn't know. So what do you call it? It's luck. But you have to seize the opportunity. I could have said, no, we can't do this problem, so we'll forget it. So I saw an opportunity and I said, I don't know anything, we'll find a problem. And we were lucky that way, but if that didn't work, we'd have found some other problem because we had the money, we could try it. So there's no, that's why I put it in quotation marks. For everybody, the definition of right is different. And if you think about your own work, it often happens that way. So, sorry. As I said, there is no magic formula.
So it's good to hear your successful stories. Do you have any failure examples?
In these problems, VLSI and all, I think we were successful. But in some of my mathematical work, there are problems which I only still have conjectures, which I gave up, and lots of other people have tried, but nobody has fully solved. So, some things just don't work out. It's called innovations problem in stochastic processes. And many mathematicians have tried and so on. Many false proofs have been published. So that's one example. And I should tell you a story about my master's thesis, if we have time. Yeah. So, I was given a problem of studying linear systems that vary with time variant linear systems. Now, I came in 57 to MIT. Lotfi Zadeh, Professor Zadeh of fuzzy logic and all these things, his thesis was on linear time variant systems, and so I said, what is there to do? He did it all. No, Wozencraft and Fano, my advisor, said, you put the communications constraints that the signals are finite bandwidth. It's not an arbitrary system. And the delays are also finite. So put the restrictions of finite bandwidth, finite delay. And what limit, so this means that linear time variant system is less general than the real problem and is more well defined. So study what can happen. And actually there's a reason why they gave me that problem. So first I found a model. I made a mathematical model of a general time event system. Very simple, as a tap delay line with taps, where the taps vary with time. Okay, you have a delay line, taps, a signal comes in, gets multiplied by the first tap, goes up, next signal comes and added. So that's the system. So this gives, a channel is not like that. Okay, I mean multi-path channels sometimes are, one path, another path and so on. But it's a mathematical model of some more complicated physical problem. So that was a good model, people were interested in it. But now they said to me, how do you identify this channel? Put a signal in and measure the signal which comes out and tell me what these taps are doing. Okay. So I tried hard on this problem for 2 or 3 months. And at MIT in those days, professors did their own work and each student did something else. So I hardly saw him every now and then. After 2 months, he asked me, so what's happening? I said, give me another problem because I can't solve it. Yeah. So he said, okay, that happens, but one can learn from failure also. So write down what you have learned and why you were not able to succeed. And in the process of doing that, I had an idea which solved the problem. So I said, one of the lessons is don't give up too soon. And learn from failure. I mean, so try to say what it is that worked. And it's a little detail, but it's a simple idea. And actually, it's called degrees of freedom. And I said, Shannon said that if you have a signal of duration t and bandwidth w, and these are large numbers, 2 TW numbers are enough to characterize this signal. That's the degrees of freedom in this signal. Okay. It's only approximate because in mathematics, if you have a signal of finite duration, the bandwidth has to be infinite, or vice versa. But infinite means what? Most of the energy is in some finite region. So I used this idea and I said, the channel has a certain number of degrees of freedom. The input signal has some degrees of freedom. If the output signal has more degrees of freedom than the channel, then you can identify. If it doesn't, then you cannot. Okay. So it was a very nice, simple idea. And actually, they were very excited about it because there's a system called RAKE. Those of you in the communications field know it's an anti-multipath system built by Lincoln Lab in 1950s. And they found that RAKE system failed. By the way, every cell phone has a RAKE system in it now. There were certain times when the system failed. And so I had a condition that the product of the bandwidth and the time delay should be less than 1 in the right units. Exactly that was when the RAKE system failed. So that was a lucky coincidence. Anyway, that then had many interesting stories as a consequence. But don't give up, no, learn from failure. That's the message. And I can give you other examples in my work also.
Well, actually this afternoon, I presented a material related to development of a new actuator systems based on twisted string actuation, so-called, because if you simply utilize electrical motor and the reduction gear system, it is very difficult to achieve high power and high speed with respect to the relatively small size of the volume. That is a really big challenge when we design the robotic manipulators or mechanical systems. So one of the ideas was coming from the idea in a conference in around 2010 in Canada. It was IEEE conference, and then we were always thinking about how to invent a new actuator systems. But one Italian team brought a great idea to achieve the very high contraction force. They just simply twist 2 strings. so that the twisted string will be contracted, but at the same time, it generates really remarkable power of, the force of the contraction force.
Yeah.
So when we see that idea, okay, that would be really nice idea to miniaturize the new actuation systems. So after coming back from the conference, we worked with my students overnight to replicate that system.
Okay.
And then we realized some big troubles to be miniaturized again.
Okay.
So we add our new ideas there. And then in the end, we could develop new actuation system called dual mode twisted actuation principle. So based on that actuation system anyway, we successfully designed very small robot finger or robot hand systems nowadays. Yeah.
I see. Oh,
So one day, okay, in the other conference anyway, the Italian team also came to me to listen to my presentation, and that they asked me, okay, how did you invent that idea? So I talked to them, okay, originally this idea was yours. So I was so surprised to see your ideas in 2010, and they replied to me that they got this idea from the historical story of the Egyptian. When they do the big construction, they use a very, very long and very thin but very long the strings. And then at the end of the string, they twisted the strings so that by using that contraction, they could move very heavy.
Yeah, you're right. All to build the pyramids. Yeah.
It's a good thing because you point out about the have broad interest to be able to cross-apply tools and perspective insights from others.
Okay. Yeah.
Thank you.
Very good. But also be alert to opportunity and seize them. Like Sailesh Rao, he could have worked on his problem, but he heard about this problem, and it made a connection. So that's how it was. It luck, but you have to be prepared to have luck, like you. Yeah. But therefore, conferences, many of them you don't understand anything, but small things stick in your head, and it's useful.
Thanks to the speaker once again. Thank you very much.
Thank you.